Hello everybody, welcome into another lesson. So today we are going to talk about logarithmic functions and their graphs. So up here I have an exponential function where you have a to the x equals y, or y equals a to the x. Well, the domain, as we saw yesterday, of an exponential function is all real numbers, and your range is from 0 non-inclusive to infinity. The idea is that no matter what value I put in for x, I will never get 0 or a negative number for y. Well, logarithmic functions, on the other hand, are the inverse functions of exponential functions. So here you see log base a of x equals y. That's how you would read it. The smaller number next to the log, that's log base a of x equals y. A logarithm is the same as saying that a to the y equals x. So this illustrates the inverse relationship between exponential and logarithmic functions. And in inverse functions, the domain and the range switch places. So your domain is going to be 0 non-inclusive to infinity, and your range is going to be all real numbers. So I could take y to any power, right? My y is my range, but my y in this case is, yes, that's going to be the range. My x is my domain. I will never get a negative or 0 value. That's how the domain and the range switch places in the logarithmic function, because it's the inverse of the exponential function. And let's first, before we graph, let's convert some logarithmic functions into exponential functions. So let's say you have something like log base 4 of 64 equals 3. So you have log base 4 of 64 equals 3. This is the exact same thing as saying that 4 to the third equals 64. So with any logarithm, you're going to take the base, set it to the power of what's to the right of the equal sign, and that'll equal the big number. So this would be 4 to the third equals 64. And let's see here. We have also log base 3 of 81 equals 4. So we have log base 3 of 81 equals 4. This is the exact same as saying that 3 to the fourth is equal to 81. They mean the same thing. And let's see, let's do another here. We have log base 7 of 1/49th equals negative 2. So you have log base 7 of 1/49th equals negative 2. Alright, so this is the same as saying that 7 to the negative second is equal to 1/49th. And we know that's true. If you take 7 to the negative second power, you'll get 1/49th. One more of this, then we'll do some natural logarithms. We'll show you those. Alright. Whoops. Log base 12 of 4. Whoops, not log base 12. That didn't make sense. I misread the book. Log base 32 of 4 equals 2/5. So we have log base 32 of 4 equals 2/5. This is going to be the same as 32 to the 2/5 power equals 4. And we know that's a true statement. So that's for basic logarithmic notation. Now remember yesterday when we introduced the natural base e. So if you had log base e of some number x, that's the exact same thing as the natural log of x. If you ever see ln of x, that means it's log base e. So that's what's considered the natural logarithm. So ln means natural log. So let's do some notations here with the natural log. Let's say I had ln of 1 equal to 0. So the natural log of 1 equals 0. Well, that's base e, so that's the same as saying that e to the 0 equals 1. And again, we know that's true. Anything to the 0 power except for 0 itself equals 1. All right. Then we have something simple like the ln of e equals 1. That's the same as saying that e to the first equals e. And that would definitely be true, that e to the first equals e. The ln of the square root of e equals 1/2. So we have the ln of the square root of e equals 1/2. Well, that is true. That would be the same as saying that e to the 1/2 equals the square root of e. Anything to the 1/2 is the same as the square root of that number. So yeah, e to the 1/2 equals the square root of e. One more for natural logs. Let's say that the ln of 1 over e to the second equals -2. So we have the ln of 1 over e to the -2 equals -2. Well, that's the same as saying that e to the -2 equals 1 over e to the second, which we know is also true. So that's how natural logs work. Now we're going to work backwards. We're going to be given some exponential notations, and we're going to convert it into logarithmic notation. So let's say we had something like 5 to the third equals 125, which we know is true. 5 to the third equals 125. How am I going to convert that into logarithmic notation? So that 5 is my base. That means I'm going to have log base 5. That's my base. And then that right-hand side, that 125, this would be log base 5 of 125 equals 3. My exponent of that base goes on the right-hand side. So this would turn into log base 5 of 125 equals 3. What if I had 8 to the second equals 64? How do I convert that to logarithmic notation? So my 8's my base, so this would be log base 8 of 64 equals my exponent, which is 2. So this is the same as log base 8 of 64 equals 2. Alright, now let's see. 81 to the 1/4 equals 3, which is the same as the fourth root of 81 equaling 3. We know that's true, right? So how do we write this in logarithmic notation? My base is 81, so this would be the same as log base 81 of 3 equals 1/4. So log base 81 of 3 equals 1/4 is the exact same thing as this. One more for regular logs, then we'll do some natural logs. Let's say I had 10 to the -3rd equals 0.001. So 10 to the -3rd equals 0.001. Well, how do I convert that to logarithmic notation? My base is 10, so this would be log base 10 of 0.001 equals my exponent of -3. Now, another interesting thing about log base 10. A log base 10 is often called a common logarithm. The reason for that is all calculators work off of base 10. If you see log in your calculator, it's going off of base 10. So it would also be correct to write this as simply log of 0.001 equals -3. If you just see log of a number, this is indicating base 10. These both mean the exact same thing as this. Now, if you have logs of other bases, in the next lesson we're going to talk about properties of logarithms, which one of those is the change of base formula. But that's not till the next lesson. And then, so in your calculator, you'll see either log, which is log base 10, or you'll see ln, which is the natural log. They're only set up for those two. So let's do some natural logs here. Let's say we have e to the third equals 20.0855 ... So we have e to the third equals 20.0855 ... So this is base e. That means it's going to be a natural logarithm. So we know this will be the ln, which means base e of that 20.0855 ... equals my exponent of 3. So this would turn into the natural log of 20.0855 ... equals 3. We'll do a few more exponentials here. Alright, let's see. We have e to the 1.3 equals 3.6692 ... So this is e to the 1.3 equals 3.6692 ... To convert this into logarithmic notation, since it's base e, this will actually be a natural log. So this is the natural log of 3.6692 ... equals 1.3. That's how you would convert that into logarithmic notation. Let's do two more of these, and then we'll move on to some other stuff. All right. Let's do one more. So let's say we have the cube root of e equals 1.3956. So we have the cube root of e equals 1.3956 ... How would we convert this into logarithmic notation? So this is base e, so that means it's going to be a natural log, the ln of the right-hand side of 1.3956 ... equals, now that's really e to the 1/3. The cube root is to the 1/3 power, so this would equal 1/3. That's exactly how you would convert that. Okay. So let's talk about some other properties with some logs here. So let's say you have something like log base 7 of x equals log base 7 of 9. So you have log base 7 of x equals log base 7 of 9. Well, the good news is if they're the same base, your logarithms will cancel out. This would end up being x equals 9. How is that though? So what you can do to cancel out your logarithms is you would raise both sides to the, you would take 7 to the power of that log base 7. So this is the same as 7 log base 7 of x equals 7 log base 7 of 9. Because if you take the power, if you take that base, raise it to the power of that log of the same base, it cancels out the logarithm, and you're just simply left with the numbers you're taking the log of. So that's how you would get that x equals 9. All right. Similar thing here. You have log base 8 of x equals log base 8 of 10. So you have log base 8 of x equals log base 8 of 10. So this is both sides are the same base of base 8. So you're going to take both sides and do that base of 8 to that log base 8 of x power, set that equal to 8 log base 8 of 10 power, which is going to cancel out your logarithms and is going to leave you with what you were taking the log of. That would just leave you with x equals 10. So that is one way to solve logarithmic equations, which in a couple lessons from now we will solve exponential logarithmic equations. We're learning some basic properties of logs today. The next lesson we'll learn some more advanced properties. Alright, now here's another thing. Let's say we have log base 6 of 6 squared equals x. We want to solve for x. So how are we going to do that? Well, there's a really cool trick with logarithms. If you have a log of a number to a power, you can bring that power down front and multiply it by the logarithm. So this would turn into x equals 2 times log base 6 of 6. Right? Okay. So that power would come down front and multiply by that logarithm. That's how these work whenever you have a log of a number to a power. So x equals 2 log base 6 of 6. Well, x equals 2 times what? 6 to what power equals 6? That would be 1, right? So x would give you 2 equals 2 times 1, which just means that x equals 2. So your real answer is going to be that x equals 2. And yes, I have more examples like that. So we have log base 2 of 2 to the negative first equals x. We have log base 2 of 2 to the negative first equals x. Well, since we're taking the log of a number to a power, that power can come down front and be multiplied by the logarithm. So this is literally meaning that x equals negative 1, or just negative of the log of base 2 of 2. Well, okay, we have the negative. Now, log base 2 of 2 means 2 to what power equals 2? That'd be 1, right? So that means x would end up being negative 1. See if we can do another example like this. Yeah, one more. So we have log base 4 of 4 to the third equals x. So log base 4 of 4 to the third equals x. Well, this is a log of a number to a power, meaning that power will come down front and multiply by that logarithm. So this is the same as saying that x equals that 3 times log base 4 of 4. Alright, so x equals 3 times, what is log base 4 of 4? So that's saying 4 to what power equals 4? That's going to be 1, right? So this would be 3 times 1, meaning that x equals 3. Let's do one more, but let's change it up a bit. Let's say I had log base 8 of 64 raised to the second power equals x. So I have log base 8 of 64 to the second power equals x. Well, this is a log of a number to a power, so that power is going to come down front, right? And it's going to multiply by the logarithm. So x would equal 2 times the log of 8, log base 8 of 64. It's the same thing. Now, x equals 2 times, what is log base 8 of 64? So 8 to what power equals 64? Well, that's going to be 2, right? 8 to the second power equals 64. So x equals 2 times 2, which means x actually equals 4. So the value of x you should get is 4. Let's do one more like this. We have log base 5 of 125 raised to the third power equals x. So we have log base 5 of 125 to the third power equals x. Well, since it's a log of a number to a power, that power will come down front and be multiplied by the logarithm. So that means x is going to equal 3 times log base 5 of 125. That's what that turns into. So x equals 3 times what? So log base 5 of 125 is the exact same thing as saying 5 to what power equals 125. Well, that's the third power, right? So x would equal 3 times 3, which would mean that x equals 9. So the value you should get is that x would equal 9. All right. So let's go ahead here now. Let's graph some things. Let's go ahead and graph the logarithmic functions. And I think I'll keep it simple and do log base 2. So f of x is going to equal log base 2 of x. We'll just go with base 2 to make life easier. So f of x equals log base 2 of x. And this is generally going to hold true for any base, whether it were 3, whether it were 5 or 10, what have you. So keep in mind though, this is the inverse of the exponential function, so it's going to look a little different. Let's start out by graphing first. So let's say I pick 1 for x. Alright, so I want my x to be 1. Well, 2 to what power? So if I put in f of 1, what is that? So 2 to what power equals 1? 2 to the y equals 1. That means my y value would have to be 0, right? So I would get the point. For x, I would get 1, 0. Now, what if I pick x equals 2? So I'm going to pick f of 2. This is the same as saying 2 to the y equals 2. Well, 2 to what power equals 2? That's 1, right? So that means y would have to equal 1, So I would get the point 2, 1, which would be right here. I'll pick x equals 4 next. So let's take f of 4. F of 4, so this is saying 2 to the y power equals 4. Well, 2 to what power equals 4? That means y would have to be 2. So I would end up getting the point 4, 2, which would be right here. Let's do one more. Let's do f of 8. Let's pick 8 for my x. F of 8, so that means 2 to the y equals 8. 2 to what power equals 8? That'd be 3, right? So y would equal 3. So I'd end up getting the point 8, 3. So that's going to be plotted right there. All right, now, what if I pick 1/2 for x? So what if I decide I'm picking 1/2 for x? So 2 to the y power equals 1/2. 2 to what power equals 1/2? That'd be -1, right? Y would have to equal -1. So I would get the point 1/2 -1, which would be right there, 1/2 -1. Let's do one more. Let's pick 1/4. So we're going to do f of 1/4. So 2 to the y equals 1/4. 2 to what power equals 1/4? That'd be -2, wouldn't it? So y would equal -2. So I would get the point 1/4 -2, which would be about right there. So you notice the further left I go, I'm getting infinitely closer and closer to x equals 0 without actually hitting it. The reason is I could take that 2 to any power, no matter what y is, and I'll never hit an x value of 0. Never. If you take a number to a power, you'll never, ever hit 0. Ever. Or for that matter, a negative number. So let's go ahead and graph this and show you what a typical logarithmic function looks like. Looks about like that. And there you go. There's your typical logarithmic function. So what is my domain? Well, first there appears to be a vertical asymptote at x equals 0, right? And that's true, because you get very close to x equals 0, but you never actually reach it. So you have a vertical asymptote at x equals 0, which tells you that your domain is going to be from 0 non-inclusive to infinity. Now, what's your range? You go all the way down to -infinity and steadily up to infinity. So your range is going to be the set of all real numbers. Now with the exponential function, it was the opposite. You had a horizontal asymptote at y equals 0. Your domain was all real numbers, but your range was from 0 non-inclusive to infinity. All right. Let's talk about reflections again. What if I took log base 2 of -x? So I'm going to take log base 2 of -x. This indicates a reflection in the y-axis. Now, generally x has to be greater than 0, right? X has to be greater than 0. How are you going to find your asymptotes and find what values of x you need that it's defined for? So take that -x, set it greater than 0. Well, this would turn into x is less than 0. So what does that mean? You still have a vertical asymptote at x equals 0. That much is true, but your domain is going to actually be from -infinity to 0 non-inclusive. So your domain is from negative infinity to 0 non-inclusive, since you have a reflection in the y-axis. So let's graph this. Let's say I make x negative 1, which would give me positive 1 inside. Well, we know that's going to be y equals 0. Now let's say we make x negative 2, which would give me a 2 inside the parentheses. 2 to the first equals 2, so that would give me a y value of 1. Let's say I make x negative 4. That would give me positive 4 inside, so 2 to what power equals 4? That'd be 2. So when x equals 4, y will equal x equals negative 4, y will equal 2. And then let's pick negative 8, which would give us y. That would give us a y of 3. All right, let's pick negative 1/2 for x, which would give us positive 1/2 in the parentheses. That would give us a y value of negative 1. Let's pick negative 1/4 for x. That would give us a positive 1/4 inside, so that would be a y value of negative 2. So here's what your function's going to look like this time. So there is your logarithmic function reflected in the y-axis from the original. So yes, your domain goes from negative infinity up to 0 non-inclusive, but your range is still negative infinity to infinity. So your range still hasn't changed. It's going to be all real numbers. All right, now what if, let's switch this around here. What if I did negative of the log base 2 of x? So I put the negative sign in front of the logarithm this time. This denotes a reflection in the x-axis. So let's start by graphing. So if I make x1, well, 2 to the 0 power equals 1. So that would be the negative of 0. You're still going to get a y value of 0. But here's where it gets interesting. What if I pick 1 for x? Well, what if I pick 2 for x? That would normally give me a y value of 1. If you negate that, you get a y value of negative 1. Alright, now let's say I pick 4 for x. 2 to the second would normally equal 4. I negate that, I'll get a y value of negative 2. And then if I pick 8 for x, 2 to the third normally equals 8. Negate that, you'll end up getting negative 3 for your y. Alright, let's pick 1/2 for x. Well, normally that would be the negative first power, but you negate that, you end up actually getting positive 1. So when x is 1/2, you get positive 1. And for good measure, let's pick x being 1/4. Normally 2 to the negative second is 1/4. If you negate that negative second, you'll get positive 2. So here's really what your graph is going to look like. So you see it's reflected in the x-axis from normal. So you still have a vertical asymptote located at x equals 0, because it'll get infinitely close to x equals 0 without actually touching it, because again, no number to any power can equal 0. And then your domain is still going to be from 0 non-inclusive to infinity. And then your range, well, still negative infinity to infinity, so your range is still the set of all real numbers. All right. And you would find all this is true, again, no matter what base you pick for your logarithm. Even if we graph the natural log of x, it's going to look very much the same. So logarithmic functions, all of it basically look the same, just like all exponential functions basically look the same as each other. Alright, now, let's do some shifting. Let's say I do log base 2 of x minus 1. Now this changes everything a bit, doesn't it? That x minus 1 indicates a horizontal shift to the right 1 unit, because if I set x minus 1 equal to 0, I get x equals 1. So that means my asymptote and everything like that shifts to the right 1 unit. So I'll actually have a vertical asymptote that's located at x equals 1. So why don't I go ahead and draw that asymptote just for good measure. That means that x will get infinitely closer and closer to 1 without actually reaching it this time. Alright, now, let's see, so that's a horizontal shift to the right 1. So that means we can't put in 1 for x or anything less than 1, but let's put in 2. If I put in 2 for x, I'll end up getting log base 2 of 1, which would give me a y value of 0. And then if I put in 3 for x, that would give me 3 minus 1, which is 2. Log base 2 of 2 is 1. Alright, next I put in 5 for x. 5 minus 1 is 4. Log base 2 of 4 is 2. Then let's put in 9 for x. 9 minus 1 is 8. Log base 2 of 8 is 3. Okay, and then let's put in 1.5 for x. That would give me log base 2 of 1/2, which would give me a y value of -1. Alright, and last but not least, let's put in 1.25 for x, which would end up giving me log base 2 of 1/4, which would give me a y value of -2. So here's what my shifted graph is going to look like. It looks very much identical to the normal log base 2 of x, except everything is shifted to the right 1 unit. So my domain this time, since it never actually hits 1, because if x equaled 1, that would be log base 2 of 0, and 2 to no power equals 0. It's undefined. So my domain would end up being from 1 non-inclusive to infinity, but my range is still the set of all real numbers, because it still goes from -infinity to infinity. Alright? Now, let's do a vertical shift. So we're going to do log base 2 of x plus 3. So I have log base 2 of x plus 3. Actually, it's probably better in this case to write it as 3 plus log base 2 of x, because it almost looks like you're doing log base 2 of x plus 3 instead. So if you want to denote a vertical shift, you probably should write the log after that plus or minus. So f of x equals 3 plus log base 2 of x means I'm doing a vertical shift upward 3 units. So let's graph this. Let's say I pick 1 for x. Well, definitely going to have a vertical asymptote at x equals 0 still. That doesn't change my vertical asymptote, because nothing to any power is going to equal 2 to no power equals 0. So my vertical asymptote is x equals 0. But what about when x is 1? 2 log base 2 of 1 is 0, so y would be 0. But I have to add 3 for the vertical shift. I would actually be up at y equals 3. Alright. Now, what about if I made x 2? If x is 2, that would be log base 2 of 2, which is 1, plus that 3 would actually give me 4. Now, if I made x4, log base 2 of 4 is 2, plus 3 is 5. Then let's make x8 alright, so log base 2 of 8 is 3, plus 3 is 6. Now, let's do log base 2 of 1/2. Well, that would be -1. 3 minus 1 is 2. Now, what about log base 2 of 1/4? That would be -2. 3 minus 2 is 1. Which means if I made x 1/8, that would be 2 to the -3rd equals 1/8. So 3 minus 3 would be 0. So I would actually have an x-intercept located at 1/8, 0. But that's going to be too hard to graph. So here's what your graph's really going to look like. So that vertical shift this time did not affect your domain. Your domain is still going to be from 0 non-inclusive to infinity. And really your range stays the same because you still go from -infinity to infinity. -infinity plus 3 or infinity plus 3 is really infinity. So your range is still the whole set of real numbers. You just simply shifted everything upward 3 units. I got one more problem and then we're going to be done for the day. Oh yeah, this is going to be a real barn buster also. So let's do this. Let's say I take -2 minus log base 2 of 3 minus x. So we're throwing everything at you this time. We're going to throw everything at you. So let's look at that -2 to start. This definitely indicates a vertical shift down 2 units, right? This is from the normal log base 2 of x. We want to describe the transformation. So you'll have a vertical shift down 2 units. Now, look at that minus on the log. That means you have a reflection in the x-axis from the original. Reflection in the x-axis. Now, let's look inside the logarithm, inside the parentheses. You have a -x inside the parentheses. We actually also have a reflection in the y-axis. And then, okay, so you have 3 minus x. If you set that equal to 0, you'll get that x equals 3. So you have a horizontal shift right 3 units. So your asymptote goes by your value of x. So 3 minus x equals 0 means your vertical asymptote is going to be located at x equals 3. So that means your x values will get infinitely closer and closer to x equals 3, but we'll never actually be able to reach them. Because if x were 3, you would have 2 to some power equals 0, which is undefined. There's no power you can set 2 equal to get 0. So here's our vertical asymptote at x equals 3. Alright, now, everything else is fair game. Another thing we have to consider is the domain. So here's the thing. X minus 3, or 3 minus x, has to be greater than 0, right? So take that 3 minus x, set it greater than 0, which would turn into -x is greater than -3. which means your real domain is that x has to be less than 3. So your actual domain is going to be from negative infinity to 3 non-inclusive. So we're working to the left of that asymptote. Your range is still going to be the entire set of real numbers. That doesn't affect your range. So let's put all this information together and graph it. Let's say I make x2. So that would be 3 minus 2, which is 1. Log base 2 of 1 is what? That's 0. So then 2 minus 0, sorry, negative 2 minus 0 is negative 2. So I would have the point 2, negative 2. All right, now let's say I pick 1 for x. That would give me 3 minus 1, which is going to be 2. Log base 2 of 2 is what? That's going to be 1. Negative 2 minus 1 is negative 3. And then, let's see. I go to negative 1. If x is negative 1, that gives me 3 plus 1, which is 4. Log base 2 of 4 is actually going to be 2. Negative 2 minus 2 is negative 4, which would be right here. And then, let's see. I'll pick negative 5 for x. Well, that would give me 3 minus negative 5, which would turn into 3 plus 5, which is 8. Log base 2 of 8 is 3. Negative 2 minus 3 is negative 5. Now let's do something interesting. Let's pick 2.5. So 3 minus 2.5 turns into log base 2 of 1/2, which is negative 1. Negative negative 1 is actually positive 1. So negative 2 plus 1 is negative 1. Then let's say I pick, all right, we'll do, let's see, 2 3/4. So 3 minus 2 3/4 gives me 1/4. 2 log base 2 of 1/4 is negative 2. Well, negative 2, negative of negative 2 is positive 2. Negative 2 plus 2 is actually 0. So here's roughly what my graph is going to look like. There's what I get from my graph with all those transformations. And you can evidently see my domain is from negative infinity to positive 3 non-inclusive. My range still goes from negative infinity to infinity. So you can get some really neat graphs even with logarithms based on the transformations if you understand what's happening. So that's it for this lesson. Next lesson, we are going to talk about more properties of logarithms. There won't be any graphing in the next lesson or the lesson after that, but we're still going to get into some very useful properties. So I hope everyone has a great day. Take care.